Let's continue our discussion of rotating type things with a new idea. Um, and that is, how does inertia affect rotational motion? Right? We've said that inertia is mass, right? Inertia is mass. Just regular old inertia is just regular old mass. So, if I apply a force to this baseball, it'll give it some acceleration. If I apply the same force, if I apply the same force to this piece of chalk, it'll have a different acceleration, right? Same force on the baseball, same force on the chalk, different accelerations. Which one has a bigger acceleration? The piece of chalk has a bigger acceleration. And of course, this is Newton's second law. A equals F net over m, right? In this form, it's easier to see the cause and effect. I apply a force, I get an acceleration. How much acceleration? It depends on the mass, right? And we call it the mass here. In this equation, it's really showing up as what we would call the inertial mass. And that's not a term I've used yet. But in this equation, this m here, we call it the mass, and that's not wrong. But in this equation, it's representing the inertia. So in this equation, mass and inertia are identical. And inertia says, how hard is it to change the motion of something, right? Forces cause changes in motion. How much change? It depends on the mass. Greater mass, greater change in motion. Now, if we're talking about rotational motion, then we have the same idea, right? An object's inertia should affect how much, torque it takes to change something's motion. But if we're talking about rotations, it doesn't just matter how much mass there is. It also matters how that mass is distributed. And so this is similar to torques, right? With forces, we just care about the magnitude of the force and the direction, right? But if we're talking about torques, then we care about the magnitude and the direction of the force, certainly, but we also care about where that force is located. A force applied farther from the pivot creates a bigger torque than the exact same force applied closer to the pivot. In a similar way, how hard it is to change the motion, the rotational motion of something, depends not only on the mass of the object, but how that mass is distributed, right? So here is my hammer again. And this hammer is not uniformly distributed. And if I rotate this hammer about this end over here, then I can feel a certain torque in my hand. It takes a certain amount of effort to wiggle this thing back and forth. If instead I rotate it about this end, well, it's much easier. And maybe you can't see it, but this is as fast as I can go here. Pretty fast. This is as fast as I can go here. Not nearly as fast, right? It's just a lot harder. And if you don't believe me, I don't know, go find a hammer and try it. But it's just a lot harder to rotate this thing from this end than it is from this end. Why? It's got the exact same mass. It has the exact same inertia. The answer is it has a different moment of inertia. In this case, my pivot is here. Most of my mass is here. And so most of my mass is at a very large radius. So this has a higher moment of inertia than this situation. My pivot is here. Most of the mass is also here. So most of the mass has a smaller radius. This is a smaller moment of inertia about this axis than this is. Same exact mass, different pivot, different moment of inertia. Another kind of fun experiment is take something with a heavy end and try and balance it on its end. And I can do that here. I know you're all very impressed, right? I can balance this hammer on its end like this. You know what I can't do? Is balance it on this end. Oh. And again, if you don't believe me, there I'm getting it a little bit. It is much harder. And you can see that I'm having to move around a whole bunch more, right? This side, if I really focus, I can actually make it pretty stable, right? This end, not so much, not so much. I'm better at it than I was when I practiced it before class. Okay. At any rate, my point is, what's the difference? Here, my pivot point is down here. Most of my mass is up here. High moment of inertia, harder to get rotating, easier to balance. Here, most of my mass is here. My pivot is here. Lower moment of inertia, easier to change its rotational motion, harder to balance. Try it yourself. You'll find the same thing. Another interesting one to try is try balancing a pencil. You can't do it. It's impossible. This is a pen, I know. You can't do it. I mean, maybe you're better at it than I am. Now do something that is longer. It has a greater moment of inertia, and you can actually balance it. Okay, so again, moment of inertia is the rotational analog to inertia. With inertia, we only care about how much mass. With moment of inertia, we care not only about how much mass, but also how that mass is distributed. Let's look at this slide. So an object's resistance to change in rotational motion, is its moment of inertia, right? An object's resistance to change in translational motion is its inertia, right? So there's this an analogy here that we're building up. So moment of inertia is the object's resistance to change in rotational motion. Its units are kilograms meters squared. It depends not only on the mass, but how far that mass is from the rotational axis. The symbol we use is an I. I should have picked a different font here. This is a capital I. For a point mass, like a rock or a string, the I is equal to mr squared. Now, for different shapes, we get different values. And so this is a chart that's just in your book. You can just look this up. If you click on the constants link within your Mastering Physics, then you'll find this chart also. So this gives us moments of inertia of various shapes. Looking at these disks, it depends on the radius of the disk and the mass. And notice we get a slightly different value here, 1/2 mr squared versus mr squared, depending on how that mass is distributed, right? Here all of the mass is distributed out on the edge. Here all of that mass is distributed throughout the whole cylinder. So we have a different moment of inertia. If these both had the same radius and the same mass, it would be easier to get this one rotating than it would to get this one rotating, because this one has a smaller moment of inertia. It would be easier to get this one stopped if it was rotating at the same rate as this one, and it had the same mass and radius. Okay, so for various shapes, we have different values, and of course you don't have to memorize these. You can just look them up. It's no big deal. The thing you need to know is that it depends on the geometry and that these formulas exist. For a cylindrical hoop, notice all of the mass is at a radius r. If all of the mass is at a radius r, then the moment of inertia is mr squared. So a point mass, like a rock on a string or a ball on a string, like in this situation here, rotating about a pivot, well, all of the mass is at the same radius, right? It's all right here. And so for this mass, that's the same as for a hoop. So that is mr squared. And I've simply listed this separately because it's not in this chart. I wish it was. So the moment of inertia depends on the rotational axis. Again, with the exact same object, I might get a different rotational moment of inertia. I might get a different moment of inertia about an axis right here versus an axis right here. So again, it really depends on the geometry of the situation, right? Where the pivot point is, where the mass is located relative to that pivot point. Now, let's say that I have a whole bunch of a collection of objects. How would I find the moment of inertia of several objects together? Like maybe I've got a disc or a hoop, and I don't know, there's a little ball attached to the edge. Maybe I've got a cylinder here, and I drop a lump of clay that sticks halfway out. How would I find the moment of inertia of both of those together? Well, you just add up the moments of inertia of all the individual things. Which, this isn't obvious, but I've got two objects here. How do I find the total inertia of my collection of objects? I'm just talking about regular old inertia from back when, chapter 3 or 4. Well, I just add them up, right? What's the total mass? You just add them up. Is there any such thing as negative mass? No. Is there ever such thing as a negative inertia? Oh, that would be weird. A negative inertia would mean I push on the object in this direction and it accelerates in that direction. Oh, that would be too weird. I can't even handle that. No, there's no such thing as negative inertia. Then is there any such thing as negative moment of inertia? Is it possible you could add something to a rotating system and have it be easier to move? No, if I add some mass to a rotating system, it's going to be harder to move, not easier to move. Always. So there's no such thing as a negative moment of inertia either. Okay, so again, it's a little bit of a stretch, right? They're enough different that it's hard a little bit to see the analogy. But if we can build up this analogy between inertia and moment of inertia, it is beneficial. All right, let's try an example. We have an object, and it consists of 3 balls shown. Oh, this looks familiar. I believe we found the center of gravity of the same thing in the previous lecture. They're connected by massless rods. Find the moment of inertia first about a vertical axis through masses 1 and 2, and secondly through a horizontal axis through masses 2 and 3. Yeah, let's just dive in and see what we get. Okay, so here is my drawing, and we're going to find first through a vertical axis through masses 1 and 2. So this is my axis of rotation right now. Okay, so if this thing was going to rotate, it would be rotating like this, about this axis. Okay. So let's go ahead and apply our equation, right? I is equal to the sum of the MR squareds. In this case, we have 3. So it's M1 R1 squared plus M2 R2 squared plus M3 R3 squared. So we'll go ahead and let's label this. We're working on A, part A. Okay, let's just plug in our numbers. Well, M1 is 1 kilogram times R squared. Ooh, R squared. What does R mean in this context? It means how far is the object from the rotational axis? Well, in this case, the object is right on the rotational axis. So in that case, R is just 0. M2, 1 kilogram. It too is on the rotational axis, so its radius is also 0. Plus M3, that's 2 kilograms. It is 1 meter from the rotational axis. Okay, there we go. 0 plus 0 plus 2 kilogram meters squared. How about B? Let's see what B looks like. Okay, so for B now, we are changing our rotational axis. Right? For B, we're not using this anymore. Now our rotational axis is through balls 2 and 3. So for part B, that is our rotational axis. Okay, so through a line right here, what do we have? We're going to still use the same equation, right? But now, what is our radiuses are what change, right? So now we're going to have I equals M1, still 1 kilogram. But now, how far is it from the rotational axis? 1 meter. Plus 1 kilogram times 0 meters plus 2 kilograms, 0 meters squared times 0 meters squared. Well, what do we get here? 1 kilogram meters. So, exact same object, different moment of inertia, y, different rotational axis. So in other words, if I had it oriented like this and I gave it a shove, it would get going a little bit faster than if I gave it the exact same shove and it was oriented like this. Because a greater moment of inertia means it's harder to change its rotational motion.